All right, so what we're going to do today then is talk about just generally how we use this analysis system. We have two main analysis programs that we use. One is called Smaart and the other is called FuzzMeasure. And the idea behind having two is they work two very different ways. So Smaart is what's called a source-independent measurement system, and FuzzMeasure is a source-dependent measurement system. The difference there is that Smaart is source-independent because all it does is compares the difference between two sounds. And it doesn't care what those two sounds are. That could be two microphones. That could be a microphone and a direct audio input from some device. It could be a microphone and a noise generator that's internal to the computer. It could be two different line inputs from two different pieces of equipment. Like it just doesn't care, right? It will just always tell you the difference between two different sounds. But because it doesn't care, that also means it doesn't know anything about those two signals. So the only thing it can do is compare in real time the difference between those two signals. But because it doesn't know anything about them, it can't sort of predict ahead of time what's going to happen. Which means it also can't tell you, it has a hard time telling you after the fact what happened before. Because it does, there's no recording of this or anything. It's real time. It's telling you in real time the difference between two active sound sources. The advantage there is it's very fast. You get the results immediately and information immediately with Smaart because it's just in real time telling you the difference between two things. The cool thing about the latest version of Smaart is that it can do that comparison of two different things on multiple pairs of signals. It used to be that you could only compare literally two things, but now you could compare conceivably, I don't know that there's a limit, but you could compare against as many inputs as you have on your audio interface or whatever and have that, but it's always comparing two things. You just could have multiple comparisons of two things going on at one time, which is kind of cool. But the other downside to a source-independent measurement system is that you always have to have that sound happening in order for Smaart to be telling you anything. So if, for example, you are relying on a pink noise generator to generate the signals that you want Smaart to compare, Smaart can only tell you information about that if the pink noise is running. If you shut it off, then Smaart loses its ability to tell you about it. Okay? And that makes a certain amount of sense when you think about it. But anybody got any ideas why that might be a bad thing?
Sometimes noise isn't happening.
Well, yes. So, but I would sort of say sometimes you don't want noise happening. Can you think of those scenarios when maybe you wouldn't want the noise happening? No one has ever been told to turn down their sound cues, when they're working on them in a space because someone's like up on a genie lift and gonna fall.
Oh, okay, yeah, like practical point of like sound cannot be happening in the space.
Right. Yeah. So like, of course, in a perfect world, we would have the room completely to ourselves whenever we're doing system tuning and stuff like that, right? But that hardly ever happens. You always have somebody else working in there, and that's okay. I don't actually mind that. I mean, I just tell them, you can be in here when I'm doing this, but you got to realize that this is actually, I don't like that we call it quiet time because it's like the absolute opposite of quiet time. It's time when we're going to make an awful lot of noise that is going to be really, really obnoxious to a lot of people, right? Either it's pink noise blaring it, really loud, or you're going to hear the same 5-second piece of music, 300 times over and over and over again. And yeah, we're going to play it again. And yes, we still need to play it again. And no, we're not ready to move on. I don't care how annoying that little piece of music has become to you now. This is what we're doing right now, right? So so that's fine. I always just tell people, you're welcome to come in and work, but I just need you to kind of work quietly. And there might be times where I need you to absolutely shut up for 30 seconds while I listen to something. But you're not allowed to complain about how loud the noises are or how many times you've heard that little 5-second piece of music. And I'm totally fine with that. But there are times when maybe you get tired of listening to the pink noise and you want to turn it off. But if you turn it off, you lose your ability to do your measurements. Right? So that's kind of a weakness of something like Smaart, which is a source independent measurement system, is that because it is not dependent on any particular source, that means that the source needs to always be on if you want Smaart to be doing any work, okay? So FuzzMeasure is a different idea. It is called a source-dependent measurement system. And the idea behind a source-dependent measurement system is that it still compares two things, but what it's comparing is whatever you captured from your microphone or your audio input, whatever, and it's comparing it against a sound that it knows it created. So it creates the sound that then it listens back for and compares against. And it's a very known and predictable sound that it makes. And so because it knows exactly what it created, it can tell, right away the difference between that and what came in on the mic. The nice thing about that is the source dependent systems tend to be a little bit better at dealing with kind of background sounds and noises and stuff, because it's easier for them to sort of say, oh, that's not anything about that. But it also means that it's hardly ever doing that in real time, because there's a fixed sort of sound that it has to generate. It sort of sends that out and then listens back for that thing to come back in, and it records it. It actually makes a recording of a period of time of audio that came in on your input, and then it saves that recording to your computer, which means the period of time that you actually need to make a sound in the room is very short, like maybe a second. You just sort of shoot a little zoop sound out there, and you have it for a second, and then the computer records it, and then you can spend your time looking at that data, right? You don't have to have that sound constantly running, because the computer knows exactly what it sent out. It doesn't have to have that sound going in order to do the math and comparisons, because it knows what it created. And therefore, you can sit there and study that material and that data for as long as you want without having to have the sound going. Which sounds brilliant, right? Great, why don't we just do it like that all the time? Any ideas? Why would we not want that scenario?
It's less maneuverable. You have to play your sound, analyze it, work with it. You can't be doing these constant changes that you can.
Exactly. So let's say that you're looking at this data and you're saying, okay, I've made sense out of this now. There's a problem that I want to fix. I have to fix it. You have to fix it and then do a new measurement and then do a new analysis. So it's a little bit slower. You can't just make the change and instantly see that the result happened. Whereas with something like Smaart, you can instantly see. If you tweak an EQ, you can see instantly the effect of that, because you're measuring in real time. Whereas with something like FuzzMeasure, you're not measuring in real time. So you sort of have to come up with a plan, you guess at what you need to do, you try to do it, then you do a whole bunch of measurements, and then you spend time analyzing it again to see if the thing that you did worked or not. And if it didn't work or not, then you got to try it again. And so sometimes that process can get really, really slow. So there are some kinds of measurements and things that are better and easier to do with something like Smaart. And then there are some things that are better and easier to do with FuzzMeasures. That's why we have both. So I'm going to take you through both of them here. So let's start with Smaart. So I'm going to open up Smaart. And when you launch Smaart, you usually will get this message which says, select a config. And what this means is the configuration, or the config, is really about how you're sort of using and linking up the inputs on your audio interface and which interface you're using. So for example, on this system, I have a little Focusrite Claret 8 Pre, which has 8 microphone inputs. and 2 analog audio outputs, and it has some ADAT outputs, which we don't use in this system. So part of the config is, hey, Smart, use that interface, not the built-in sound card on the computer. But then the other thing it has is, hey, here's the sets of inputs that I want to compare and all that kind of stuff. Here's the kinds of measurements we want to do. That's all part of the config. Now, if this is your Smart system and you do the same kind of measurements all at the same time, and you just sort of like have a process that works, then maybe you would have a config that you would just sort of use all the time. And you don't have to repeat that work. I would say in most cases for our class, we're probably going to make a new config every single time. For a couple reasons. One is that I need you to learn how to do it. And practice makes perfect. So we're gonna make a new one every week. But also we're going to be doing a different kind of measurement every week. So we are probably going to need different configurations. So I'm going to say create a new configuration and click OK. And so it's going to say, all right, what do you want? This is the configurator, this window that comes up. The configurator, the first thing that it asks you is, which input devices do you want to use? And it shows you in here the audio inputs that are available on your system. So you have Core Audio built-in microphone, that's the built-in mic on the computer. You have Core Audio Focusrite Thunderbolt, that's my interface that I have, my big interface that has the 8 mic inputs, so I definitely want to use that. And then there's this other one called generator. And what the generator is, that's a pink noise or sound generator built into Smart that you can use as an input device. And that's in the grand scheme of the history of Smart, that's a relatively new feature. It's one that I have found to be not as helpful because it's harder to kind of like balance out the levels I've found. I mean, it's possible to do it, but I'm kind of like from the old guard of Smart that, from before that feature was, and we figured out other ways to do this, and so I'm more comfortable with that. But I know people that like to use the generator all the time. It's just not something that I find particularly useful, so I'm not going to teach it to you because you're paying for my opinion. And my opinion is it's better to not use the generator. So I'm not going to check that. But, if you want to play around with that, you can. And then when you check the Thunderbolt thing, it's going to say, okay, which inputs do you want to use? Which inputs do you want to make available to Smart? I certainly want the first 8 because those are the analog mic preamp inputs. So I definitely want those. I don't need any of these digital ones because I don't need them. And then output devices, you get the same thing, built-in output or Focusrite. I'm just going to uncheck the built-in output, so I don't need that. Outputs you want to make available. We're really only going to use output 1 and 2. So I'm just going to uncheck the other ones just so that my menus will be simplified later. How are we doing? Everybody seeing what they need to see? You getting enough detail on the screen? Okay. Question? Okay. Okay, so the next tab here is measurement config. So this is where you tell Smart in the configurator what sort of measurements you want to do, what you want to set up. It defaults for some reason that has never entirely made sense to me, and I really should talk to the people at Rational Acoustics about this. Like, why does it default to 8 spectrum measurements? Because the spectrum measurements are the most useless thing about this program. So why would it give me 8 of the most useless part of it? I don't understand. So I'm going to delete those. So, and for some reason you can't select more than one at a time. So I just have to select and delete the ones that I don't want. I will leave one just so I can show you why it's stupid. And then we don't ever have to speak of it again. Okay, so one spectrum measurement, just so that I can be snarky. And then we're going to make a new measurement called a TF measurement. TF stands for transfer function. Yeah, the transfer function is the thing that compares 2 inputs, okay, which is what we want to do. And in some systems, some of your measurements, you might make multiple TF measurements, okay? We're just going to do one today to keep things simple. So a new TF measurement, and it's going to say, okay, what do you want to call this measurement? it doesn't matter what you call it. You can call it anything you want, but you probably should call it something that'll help you know what it means, especially in a measurement system where you're going to have multiple microphones. You have to decide what you're going to call these. So you could just call it the microphone 1, or you could call it the thing that you're trying to measure. Like if this is the mic next to the front fills or something, then you might call it front fills, or you just decide what you're going to call it. Just for sake of simplicity, today I'm going to call it input 1, or actually mic 1, because it's the only mic I have and it's plugged into input 1, and that will help me not get confused. So then it says you have to select a measurement channel and a reference channel. The measurement channel is the thing that you are trying to get information about. Okay? So it's the thing you're trying to get the information from. And I want to get the information from input 1 because that's where my measurement mic is. Let me show it to you. There it is. So I have this little measurement mic set up, pointed at this speaker, and I want to hear or see in Smaart information about what is coming out of the speaker. So I'm going to shoot the speaker into the mic, and then I want Smaart to tell me what is coming in on that mic. So the measurement channel is the mic, okay? Now, the reference channel is the thing that you want to compare against. And the thing you want to compare against is some known source. So something that you already know something about. This ought to be like some sort of perfect source, or theoretically perfect source that is not, messed up in some way by acoustics of the space or whatever. Now I'm going to select input 8. Here's why I'm going to select input 8. Because remember when I said that Smaart has its own noise generator? And when I said that I don't like to use it, that was not entirely accurate. What I meant by that is I don't like to use the generator as an input device, but I definitely like to use it as an output device, because what the generator does is it spits out pink noise or whatever sounds you want, and it'll shoot it out of a physical output of your system. And then what I'm going to do is, because I have 2 outputs of my system, one of them is going to go into the amplifier that then drives the loudspeaker, right? And then the other output is literally going to go back into the audio interface. So I have the second output from the interface that is called a loop back, and you just loop it back into one of the inputs. So I have the second output of the Focusrite plugged into input 8, which basically means Smaart generates pink noise, shoots it out of these 2 outputs, and then I listen to those 2 outputs in 2 ways. One is I send it into the amp from the speaker, and then I send it into an input of the device. So it's listening in real time to what it's spitting out. The reason I prefer that to using sort of the software loop back in there is now I get to use the input preamp to adjust the input level of the pink noise without having to change the level that it gets sent out to the loudspeaker. Okay?
So Jason, the second input, the one that you're looping back into your Focusrite or whatever their interface is,
yep.
You're doing that so you can get more individual control on the level of that going back into your device, right?
Exactly, yeah.
Why is that, like where is that signal going? Why do you need more control on that level?
So you'll see that it'll become more clear when we do the measurements, but part of getting these measurements to be really good is you need the 2 signals that are going to be compared. You want them to be coming in at the same level, or if not the same level, some difference in level that is meaningful. And because the difference in level affects the data that you get.
So the signal that's coming back into the system, back into the computer, not going through the system being measured by the microphone, is going to be compared back against the signal that the microphone picks up. Yeah.
Exactly.
Gotcha. Okay.
So, sorry, somebody had a question?
Just doing the analog loopback also means that any acoustical or electronic properties of the interface, like any magnitude changes in frequency response or delay changes.
Oh, those would both be reflected. Yeah.
And none of those affect your measurement.
Yeah, so like theoretically there should be, there should be nothing that happens to this sound as it's going through this little wire that's looping back into the computer. right? The only changes that really should be happening is potentially the level, because I might adjust the input gain when it comes back in. But other than that, it should be pure, right? It should be, you know, there's no reflections, there's no like distortion or smearing or any weird stuff that would affect my data. So what I'm saying is I have this thing that is theoretically a pure pink noise source. And I'm asking Smaart, tell me the difference between this pure pink noise source and the thing that I'm hearing on the microphone. And the thing that I'm hearing on the microphone will be different, right? Because it's going through an amplifier and then a loudspeaker and then out through the air, and it's bouncing off of walls and stuff, and it's gone through a crossover. And so Smaart will be able to tell me and show me all those things that happen to it, because those things will create differences in the sound. Sometimes very subtle differences, but differences nonetheless, and Smaart will be able to see them. But if the level is vastly different between those two signals, then I may not be able to see the detail that I need.
Okay, I have one more question about the tone. You were saying that pretty much it could be like any pure tone, like anything that, like, is there a disadvantage to using like a sine wave other than it being unpleasant, or like?
Well, a sine wave will only show you a single frequency. And
right, yeah, pink noise is full frequency, yeah.
Yeah, so in some cases, a sine wave is helpful, right? Depending on what you're trying to measure. But if I'm trying to get a sense, like in this case, I just want to get a sense of what this loudspeaker does. I would get a much clearer picture all at once using something that was more broadband. But it doesn't have to be pink noise. It could be a piece of music, right? A recording. If it's a recording that sounds good, it's got a lot of information in it, you could use that. Another thing that some people do to kind of like, you know, make all the people that are in the room that are trying to get work done feel better is you play music and then you put a little bit of pink noise underneath of that and you mix that together. So it's like music with sort of like quiet pink noise inside of it. And that helps fill in the gaps that might not be there, you know, that might have some missing information in the piece of music, so that Smaart has a full set of information to work with. That's another little trick. I've used that sometimes. But yeah, it literally could be anything. That's one of the advantages of Smaart, is you can use literally any audio signal to do this comparison with. Okay, so I've got this measurement set up. It's mic 1. I'm using the Thunderbolt interface. Measurement is input 1, which is the mic, and the reference is input 8, which is the little loopback thing. So I literally have a cable, a 1/4 inch to XLR cable that is like, the 1/4 inch is plugged into the output of the Focusrite, and the XLR is plugged into the input of the Focusrite. It's just, it's like a 6-inch cable that just loops right back in. So I'll click OK, and there it is. Now I have it. SPL config, I'm not going to worry about that yet. I'll just click OK here. Okay, so now I've got Smaart. Okay, so here's what I want to do. I want to first show you this first mode. So if you look down here, oh, hang on. Let me turn on my little zooming effect here, so I can zoom the screen. Oh, there we go. Okay, this should work now. Oh, wait, why is it doing like a weird spotlighty thing? Fix that. Try that again. Oh, Zoom Star full screen, that's what I want. Okay, now let's try it. Hey, there we go. Okay, so down here in the bottom right, can you see the zoom? Is it zoomed in for you? Okay, so you see how you've got spectrum, transfer, or live.
Jason, are you asking if it's doing the zoom to your cursor?
Yeah, no, I mean like zooming in the screen.
Yeah, it's not doing the spotlight view on the cursor.
That's a bummer.
I mean, I can still see it though.
Okay. Well, anyway, I'll figure that out later. Okay, so down here at the bottom, you see you've got spectrum, transfer, or live IR. IR stands for impulse response. Spectrum is that thing that I told you was stupid. So I'm going to show you what that means right now. So I've got input 1 and input 8 right now set up as spectrum measurements. So I'm going to hit the play button for input 1. And what that's going to do is it's going to show me what's coming in on this mic. So let me just kind of turn up the gain here a little bit, and you can see what's going on. So it's picking up my voice from, you know, over here, and it's just kind of showing me in real time what's happening. Now, there are some settings here I can do. Right now, it's kind of doing a pretty slow averaging. So let me speed that up a little bit. And then it's got some banding here that I can do. So I can say, let me just say no banding. So now this is just like full resolution, what is going on with this thing. And it's showing me what's happening, basically how loud every frequency is at this point in time. So let me turn on the pink noise and let you see what that looks like. Okay. So let me band this a little bit. Okay, so that's what that looks like with pink noise. So the reason I think this is useless is all this does is tell me how loud every frequency is that's coming out of the loudspeaker right now. The reason that that is not useful is because, you know, is that right? Is that wrong? Is that what's supposed to be happening? Is that not what's supposed to be happening? You have no way of knowing. It's just telling you what is happening. This is happening. But just because that's not a flat line or anything doesn't mean it's wrong. And so it's an incomplete set of information. The only thing that I've ever seen anybody use this for that is even remotely useful is that when you get a feedback frequency, you will see that sine wave spike on this spectrum view. And that can be really helpful for people who like to use EQ to solve their feedback problems, which, as you know, and I taught you last year, is the worst way to solve your feedback problems. But if that's the way you want to solve your feedback problems, then this is a good way to find out really quick which frequency you want to take out, along with the 3 million other frequencies that you're going to take out when you're notching this out. So the spectrum view will show you right away, zoom, this frequency jots out because it feeds back. That's about the only thing useful I've ever seen anybody do with spectrum view. Other than that, it just looks cool. And so a lot of people like to just have it on because it looks cool, but it doesn't actually tell them anything useful. So that's my opinion about that. And I will not apologize for it because I believe I'm right. But you will see a lot of people will just turn on spectrum view because they think it looks cool all the time. And I really have no idea what they think that information is helping them accomplish. Because it's just telling you what is happening. It's not telling you that it's right. It's not telling you that it's wrong. It's not telling you what it means. It's not telling you why it's happening. These are all the parts of, all that information is missing. So anyway, I think it's dumb. I don't know why that's the default and why they give you 8 of them. Why do they give you 8 of them? Just because that's how many inputs you have in it. It just doesn't make sense to me. All right, so here's what I do think is useful, transfer function. So transfer function is the part where you actually compare two things, okay? So before we get this going, I want to show you something. So let me pan the camera over here. So this is an analysis microphone. It's a very special microphone. Why is it special? Because a couple of things. What makes a good analysis microphone is that there's nothing inherently special about it from the sense of like, it is just a microphone. It's a condenser microphone. But the things that you want in an analysis microphone is you want it to be a relatively flat frequency response, as flat as you can. Not all microphones have a flat frequency response. And that's not bad, right? An SM58, for example, does not have a flat frequency response. And yet it's one of the most popular mics used out there. Why? Because the natural frequency response that it has sounds good for a lot of things that people like to use it for. But it is a very not flat microphone. And the reason that you don't want that for an analysis microphone is that if, let's say, I want to find out the frequency response of my loudspeaker, and so I shoot some peak noise out of that, and if I use the SM58 as my measurement mic, Smaart would then compare that, and it would tell me, oh, Jason, this loudspeaker has this big boost there at around between 2 and 4 kilohertz. And I would think, oh, that's kind of weird. I should start EQing this loudspeaker. But in reality, that big boost is happening at the microphone. Right? So I would spend all this time trying to fix a problem with my loudspeaker that is actually happening in my microphone. So you sort of don't want a measurement microphone that has, you know, dramatic changes in frequency response. You want something that's relatively flat. One of the best ways to make a microphone have a flat frequency response is to make it omnidirectional. Because one of the reasons that the SM58, for example, has a not flat frequency response is because the things that they have to do to the mic to make it cardioid, to make it be really sensitive this direction but not sensitive the other direction, that thing they have to do to make that work affects the frequency response. So the best way to make it be a flat frequency response is to make it omnidirectional, to not try to make it a directional mic. And that basically means sealing it, you know, all around. So you don't have any vents or ports on the side like you do with other ones. So that tends to make it omnidirectional. The other thing that you have to do to make it omnidirectional is you want the diaphragm on the end of it to be very small. Anybody know why? They got to guess why having a small diaphragm would help it have a flat frequency response?
I mean, I know it's about wavelength. I've got that much. It
is about wavelength. Very good. What is it about the wavelength that anybody got any guesses? I'm going to stand closer to the mic here. Okay, so what would wavelength what would wavelength do? So we know that the size of the diaphragm is connected in some way to wavelengths of frequencies, right? What is that connection? Anybody remember? We talked about this last year.
Well, I mean, like a higher wavelength, or a smaller wavelength is a higher frequency. A smaller diaphragm is better at reproducing those in the way that a larger diaphragm would be better at reproducing or receiving.
Not necessarily. You're on the right track. It's not that the large diaphragm can't produce.
Well, yeah, like it'll still, but
it's about the directivity. Okay, remember when we talked about directivity relative to the size of a diaphragm of a loudspeaker?
That you cannot control low frequency.
Yeah, so as the wavelength gets bigger than the diaphragm of the driver, then that driver starts becoming omnidirectional for that frequency.
You keep the diaphragm really small and then they'll all be omnidirectional.
Yes, so that is how you make it omnidirectional. One of the other ways you make it omnidirectional is making the diaphragm very small. If you can keep the diaphragm very small, then it stays omnidirectional even at really high frequencies. So like that big studio condenser microphone that has like an 1.5 inch or 1 inch diaphragm, capsule on it, it sounds lovely, right? You go right onto it and it sounds great, and it's picking up those high frequencies just fine, picking them up really well. But even if you switch it into omnidirectional mode, like let's say it's an AKG C414, right, that has a switchable polar pattern on it, that's a big diaphragm on that mic. Even if you switch it to omnidirectional mode, it is still directional at the really high frequencies for any frequency whose wavelength is somewhere around 1 inch or smaller. Okay, so that would not be a microphone to use as a measurement mic because of that, even if you put it in omnidirectional mode. This, however, will be very flat, even up to high frequencies responses, because it'll be omnidirectional. And remember, it's the omnidirectional that makes it be flat. Okay, so that's kind of what you're looking for in an analysis microphone. The other thing is, depending on how much money you spend on the analysis microphone, of course, it will never be perfectly flat, no matter how much money you spend on it. But the more money you spend on it, the more likely the manufacturer is going to take the time to figure out the imperfections within each microphone. So this is probably a $700 Earthworks microphone. And that's enough money to spend for Earthworks to kind of keep track of the microphones individually, So each microphone gets an individual serial number, and when it comes off of the manufacturing line, they actually measure every single microphone. And then they send you the frequency response of that microphone. Not just that model of microphone, but your microphone. Your microphone that you spent $700 on has this exact frequency response. And that will be different than the next Earthworks microphone that comes off the line. Will have a slightly different frequency response because of imperfections and components and manufacturing and all that kind of stuff. And so they will measure that second microphone, and they will, let's say you buy 2 of them. They will send you a chart that says, here's the frequency response for your first microphone, and here's the frequency response for your second microphone. And they might be a little bit different, okay? Why that's useful is that if you're doing really, really specific measurements that are very detailed, then you may need to account for those slight variances in the microphones. And both Smaart and FuzzMeasure have the ability to load up a reference frequency response file. So you can sort of load it up and say, here's the frequency response of the actual microphone I'm using for the measurement. And then Smaart and FuzzMeasure will compensate for those imperfections and not let those affect your data. Now, we are not in a situation where we're doing those kind of measurements where we need that kind of detail. So we rarely will have the need to pull out actual reference files, but it's possible to do. So that's that microphone. There's another one. Well, I've got another set here in the cabinet here. These are 2 microphones from a manufacturer named Josephson Engineering. These are a matched pair. And what I mean by a matched pair is, as they come off the line, they measure every microphone, right? And when they're able to find, just like by chance, 2 microphones that happen to come out really, really close to each other, like so close to each other that they may as well be the same, they will pair those together and they'll sell them as a set. And of course, you pay extra money for that. You pay extra money for that happy accident. But the advantage there is, if you don't want to go to the trouble to load up the reference files and everything, you at least can use these 2 microphones and do comparisons against them. And you know that even though these 2 microphones are not perfect, they are at least alike in their imperfections, right? And therefore, if you do a comparison using the 2 microphones, you know that what you're seeing is actually happening, and you're not seeing colorations because of the mic, because the mics have the same flaws. Does that make sense? So that's why I have these 2 microphones, is they are a matched pair. They are one of those happy accidents that came off of the manufacturing floor. They went, oh, look, these came out almost the same. We should charge somebody more money for those, right? Because we accidentally made 2 identical mics. So you pay more money for that. I also have 3 of these. Now these come from a company called Audix. They are the TR40 microphone. This is a really inexpensive microphone. I think it's like $100 maybe for this mic, okay? It does not have, they don't measure each of these microphones when they come off the line. They don't send you config files for each one. But it is a relatively
piece of trash.
Yeah, I know. But it is a relatively flat frequency response mic. It is omnidirectional, and it was only $100. So why would I have some of these? It's like, well, for a couple of reasons. One is that someday you're going to be out in the big wide world, and you're going to need to start doing this kind of stuff yourself, and maybe you're going to get in a situation where you need to start buying your own gear. And you'll see through the course of the semester, we'll use these mics every once in a while, and you'll see they work just fine. They're not as great as the fancy, really expensive ones, right? But they're fine. You can get a lot of really good work out of these inexpensive microphones. But the other reason I have these is that sometimes we're measuring things that don't rely on frequency response. Sometimes I'm measuring time. Like maybe I'm setting up a presence delay system and I just want to find out how long it takes for sound to get to different parts of the theater. I don't need to put 10 $700 Earthworks microphones all around the theater to find out how long it takes for the sound to get to each of those microphones. You know, a $100 microphone will tell me just as much information about time as the $700 microphone will tell me. They will both tell me exactly when the sound hit the mic. Now, you know, the quality of that sound hitting those two mics might be different, but they will hit at the same time. And so there's no point in spending all the money on a fancy microphone just to find out when the sound got there, okay? So I have 3 of these little cheaper microphones just for that purpose. It's like, okay, we just need to put a few more microphones like over in the back row to see how long it takes to get to the back row. It's like, all right, great, just put one of these cheap ones out there and we'll know real quick. Okay. Here's another little pro tip. Someday, when you're out there doing like summer stock theater in a cornfield in Kansas, and you know, you're thinking, there's something going on with my sound system and maybe I want to measure it. But you're in a cornfield in Kansas and there are no measurement mics, you know, to be acquired or purchased anywhere in there, and you don't have time to like go buy something or order it on, you know, online or something. Can you think of another kind of microphone which is probably going to be readily available to you that would meet the criteria that I just described?
A log?
Yeah. So, you know, most of the small microphones that we put on actors are very small diaphragm, omnidirectional, and fairly flat frequency response microphones, aren't they? So, and you probably have a whole bunch of them sitting right around, even in a cornfield in Kansas. The disadvantage to those is they probably have to plug into a wireless transmitter, which means, you know, you're not using a cable to hook up, which there will be some problems that get introduced to the signal, namely the companding that happens with the microphone, because that transmitter will compress that audio dynamically before it transmits it over a frequency, and then the receiver will expand that dynamic range back out, and there will be artifacts as a result of that. But, you know, for purposes of like tuning a sound system in a cornfield in Kansas, those slight imperfections are not important, right? Like, you'll get the information you want. You'll be able to get a general sense of the frequency response you're dealing with. You can certainly measure time, all those kinds of things. So that's just a little pro tip. I have tuned entire sound systems using lav mics before, and it worked just fine. Job got done. Okay. Last thing I'll say about the microphones is these are expensive microphones, and we don't want to drop them. So, especially not on this concrete floor. So when it's your turn to be here in the room working with us on this, and I say, hey, go get a mic out and put it out there, you know, if you're gonna like put the little clippy on, take the mic off the clip first, and either hold it securely in your hand or set it somewhere securely, and maybe even unplug it from the cable and set it securely. And then you can put the clippy on separately, so that if the clippy falls off when you're trying to spin it, the microphone doesn't tumble to the floor, right? And then once you get it on, then you put the mic on, and now it's secure. Okay, so just be careful with these mics. They sort of stop being the thing that the little piece of paper says they are, you know, the more times you drop them. So we spend a lot of money for that little piece of paper, so we want it to stay meaningful as long as we can. All right, any other questions so far? All right, let's start doing some measurements, shall we? Okay, so the first thing I'm going to do is just kind of show you generally how a measurement is done. So I've got, I'm going to turn on the pink noise, and I'm going to turn on the mic. Okay, so the first thing maybe I want you to watch is over on this right area, you want to look at those 2 meters that are coming in on the 2 mics. And the green one is the microphone, and the blue one is the loopback cable. And we want these to be as close to the same level as possible, okay? So I'm going to turn the pink noise back on, and let's look at what's going on there. So they're a little bit different. So what I'm going to do is I'm going to turn up the input on the pink noise.
Jason, this probably isn't the most relevant question, but what are you playing the audio through towards the microphone?
Oh, I can show you. It's a D&B Q7.
Very nice.
There, yes? Okay. I'll zoom out and you can see the whole thing. How about that? Okay. Okay, so the way you know that you've got this right is this green line in the bottom should kind of line up more or less on this vertical center where it says 0. That's how you know you've mostly got those levels lined up, okay? So that's the first thing. So let me show you, let me just talk you through what you're seeing here. So this green line down here at the bottom is called the magnitude response, which I will probably most of the time just call the frequency response. What this is telling you is the difference in magnitude per frequency between the two sounds, okay? So when you see, for example, this little part that is a little bit of a peak that says it's around 1.3 kilohertz, what that's saying is that 1.3 kilohertz is coming into the mic about a dB louder than it's coming in off of the loopback, right? Whereas 1 kilohertz is coming in at the same level at the mic as it is on the loopback. And then like over here, it's saying 47 kilohertz is coming into the microphone 7 dB quieter than it's coming in off of the loopback, right? So it's telling you the difference in magnitude between each frequency as compared with those two inputs. Up here in the middle, this is your phase response. And what phase response is telling you is this is the difference in phase between, for each frequency compared, against what's coming in off of the input 8 and what's coming in on the mic. Now, where would these phase different, this is what we're seeing right now is a big difference in phase. If the phase was perfectly lined up, this would be a flat line. So why are we seeing such a jagged line here for phase? What would cause that to happen? Any ideas?
It's a concrete warehouse that you're in.
Well, so yes, there could be sometimes reflections can mimic phase problems and make Smaart think that there's a phase issue. So that could be happening here. Maybe. Any other ideas? No ideas. Okay. So what is phase?
It's
Anybody
time.
Yeah, it is basically time. It's a bit more complicated than that, but a working definition is that phase and time are very closely related in sound. And so when we see that there are vast differences in phase, that should tell us that there are probably also some vast differences in time. Okay, what would be causing a vast difference in time here between these two signals?
Any kind of latency in the system.
Yeah, so where would we be getting latency?
Cables, your processors.
Yeah.
Software too.
Air.
Yeah.
Sure.
Air, literal air.
Yeah, exactly. So we've got this sound, this pink noise is coming out of the audio interface. It's going into this amplifier, and the amplifier has a digital processor in it, which means it's probably going to pick up, a millisecond of latency, right? It's going to take this amplifier a millisecond to get the sound out. So there's a millisecond we've picked up in latency. Then it gets into the loudspeaker. The loudspeaker will have a certain amount of timing issues because of just the way the drivers move. The drivers are not going to move perfectly synchronously for every single frequency. Each frequency will be kind of pulsating at a slightly different phase just because of the mechanics of the driver, right? That's just how that works. So there's a little bit of like, you know, that's, strictly speaking, that's not time. That's not a time problem. That's just a mechanical problem of how the drivers oscillate, and they just oscillate frequencies at slightly different phases. That's a really difficult problem to solve. And some manufacturers will spend a lot of time trying to solve that problem. Some don't care a whole lot about that problem. And there's a huge debate out there as to whether that problem matters. So that is part of what we're seeing here, but it doesn't account for all of it. But we've certainly accounted for at least 1 millisecond of time here. We know we're losing a millisecond going through the amplifier. And then somebody said something else. What was it?
I mean, we said a lot of things: cables, air, computer.
Yeah, so the cable is probably not introducing a noticeable amount of latency.
Yeah, that's a 6-inch cable.
It would be, well, you know, even the long XLR, I mean, that's going to be pretty close to instant. I mean, there are a little tiny bit of latency, but nothing that's going to be super noticeable. But the air is probably the biggest one. How much air do I have that I'm dealing with here?
Like so much.
A lot, quite a lot.
Like so much.
At least 10 square feet.
10 air.
10 cubic centimeters.
Right? You see this air between the loudspeaker and microphone? That's going to take a certain amount of time for the sound to get from here to there. How much time? I don't know. This looks like 1, 2, 3, 4, 5 feet or so, 5 or 6 feet. So we would expect at least 5 or 6 milliseconds, right? For the sound to travel that distance, plus the millisecond that's in the amp. So there's about 7 milliseconds of time that we've accounted for that is probably going to be different between the two sounds here. And that would certainly explain a huge impact on the phase response. So let's take a look at how we could fix that. Let's start by just guessing. Let's take our educated guess and see if we can fix it. So what I'm going to do is I'm going to turn the peak noise back on, and then you see this little number here that says 0.00. That is delay. And what I'm going to do is I'm going to delay the reference signal. So I'm going to delay that loop back, because that's theoretically coming right away. There's not noticeable latency there. There's maybe a little bit on the input-output, but we are going to assume for a working theory that that is probably already 0. So, and the sound that is hitting the microphone is happening, we think, probably around 7 milliseconds later, right? Just based on our little guess here. So what I could do is I could actually add 7 milliseconds of delay to that reference channel, which would back it up to line up closer to where the mic is. So let me turn this on, and I'm just going to slowly add time in, and let's see what happens to our frequency or our phase response. Let me put 1 millisecond in. Oops. I'm going to just go straight to the 7 milliseconds. Ooh, look, it's getting better. Less jagged lines. I'll slowly add some more in here. We go to 8. Let's try 6. Ooh, 6 is even closer. Okay, so I tried 6, and I got a lot smoother frequency response, or phase response, right? So we know we're probably right. Now, here's the good news. You don't have to do that math every time. You don't have to measure everything. Smaart will figure it out for you. There's a little shortcut here. And the shortcut is this little find button. Okay, so what I'm going to do is I'm going to turn the peak noise back on, and then I'm going to hit the find button. And what Smaart is going to do is it's going to attempt to figure out the difference in time between the two signals. And then it's going to show you its best guess. It's going to say, I think there's this much time between these two signals. And if I'm right, I could introduce that much delay on the reference channel and these things will line up, okay? Your best thing to do before you hit that button is to think in your mind, what sort of number do I think I'm going to see? Because sometimes Smaart will tell you a ridiculous number. And the only way you know that it's ridiculous is if you've thought about it ahead of time and get an idea in your head of what kind of number this maybe ought to be. So we know that this number is probably going to be somewhere in the range of 6 milliseconds, right? 6 to 7-ish milliseconds based on our guesses. So let's see if Smaart gives us a number that's in that range. So I'm going to turn the pink noise on and then I'm going to hit find. Okay, it says measured delay 5.6 milliseconds. That's in the range of what I would consider reasonable, right? So I'm going to hit insert. So I put 5.6 milliseconds in, and look what happened to my phase response graph. It smoothed out quite a bit, okay? So that is probably the most common mistake you're going to make when doing Smaart measurements, is you're going to forget to do that delay compensation, and then you're going to have all kinds of wonky data, and you're not going to know why. Or you're going to guess wrong the reason why, and start making all kinds of changes to your system to fix a problem that has nothing to do with your system. It has everything to do with your actual measurement. So here's another clue. Let me go back. I'm going to take this delay off, and I'm going to measure it again. Okay, you see this red line here under magnitude response? This red line stands for something called coherence. And what coherence is doing is it's basically, the way I like to think about is this is a confidence meter. So this is Smaart's confidence meter. And by confidence, I mean how confident is Smaart that it's giving me good information? If Smaart is very confident, then this red line will be at the top of this magnitude window. If Smaart is not very confident, then this red line will be down here towards the middle of this window.
So what is it basing the confidence off of? Like, what does it look at to determine what confidence is? Is it fidelity?
Well, it's looking at time, right? So it's seeing, because sometimes it might be hearing this sound more than once on the microphone, right? It might be hearing reflections off of surfaces and stuff like that. And it's like, how confident am I that I've zeroed in on the right version of this? Because like if it hears it 5 times, it has to guess which of those 5 is the path that you're wanting to measure.
Okay, so it's not as much like confidence increases due to good data, but decreases due to a lot of other factors.
Yeah, so it's basically trying to say like, okay, I'm hearing this a lot of times. I'm pretty confident that I have picked the right one. Or I'm pretty not confident that I've picked the right one. Or it could be that, you know what? There is such a ridiculous variance of phase here that I'm really not sure. Smaart, I'm not confident that what I'm showing you is real. Okay, so what we're seeing here is pretty good confidence in the 60 hertz to 2 kilohertz range. It's pretty confident about that information. Between 2 kilohertz to 10 kilohertz, it's starting to have doubts. Okay, and then from 10 kilohertz and above, it's sort of like, I have zero confidence that what I'm telling you is true. Okay? And if you think about it, when you see this kind of thing happen, really high confidence at low frequencies, but low confidence at high frequencies, that is almost always a time problem. That is almost always a problem because you forgot to line up the delay in your measurement. because as that delay shifts, it's the high frequencies that get affected first, because they're the ones that start comb filtering, right? A little tiny bit of delay will comb filter the high frequencies before it can comb filters the low frequencies. So when you see confidence take a dive at the high frequencies, odds are you've got a delay problem. Okay? So the point of the confidence meter, though, or the coherence meter is what it's actually called, the coherence graph, is that helps you know how seriously to take that information. So for example, there is, Smaart is telling me that there is a little dip here around 360 hertz in my magnitude response. But that dip at that frequency lines up with a dip in coherence as well. You see that? I've got a little dip of coherence around that same frequency. That would tell me that I should maybe not get too worried about that little dip in my magnitude response, because Smaart is saying it's not even sure if that dip is real. Okay? And so I'm not going to worry, I'm not going to lose a whole lot of sleep over that little dip if Smaart isn't confident that it's even happening. That make sense? So, okay. So now let me go ahead and fix the delay again. And there we go. So now I've got it, and you see now my coherence went way up, right? I've got pretty good coherence for almost this entire measurement, so I'm probably doing pretty good data. I've only got a few dips here and there, which are probably the result of reflections. There's probably a reflection going on that is resulting in a weird phase thing happening for a certain frequency, and that's making Smaart not sure about that frequency, thinking, I'm not sure how good this is. That's probably what's happening. But generally speaking, our phase response got a lot better. Our frequency response got a lot smoother. There's some options here for how to look at this information. So you have this concept of averaging, and let me show you what that looks like. Oops, I don't want that. Right now it's set to slow. Let me just turn off all of the smoothing and all of the averaging, and let's see what we end up with here. Okay. Oops. So this is what happens when you have no averaging and no smoothing. So it's just kind of showing me in real time what's happening every little millisecond, what is happening. And we know that like sound is just all over the place and it's varying greatly all the time. So you usually want a little bit of smoothing and a little bit of averaging just to kind of slow this thing down a little bit so you can get a sense of the trends, right? Because the computer has the resolution to see things moving that fast, but our ears don't. Our ears respond to the averages of things we hear, not to the little instances in time. That's what that concept of like RMS is all about. You know, and the concept of like headroom and crest factor and things like that we talked about last year is that what we hear, we tend to not hear the peaks of the sound. We hear kind of the average level. And so even though it's just because Smaart has the ability to hear the peaks and analyze those, doesn't mean you should spend a whole lot of time staring at that information, because that's not information that affects what you hear. So the first thing to do is turn on the averaging. And the averaging would just be like, just slow this thing down a little bit, right? Just show me the average of what's happening on all these graphs. And you can decide how much averaging you want to do. If I just turn on fast averaging, this is what I get. Okay, that's better than what I had before with no averaging, but it's still a pretty rough graph. It has this thing called slow averaging. Let's turn that on. Okay, now my graph is a lot more stable, right? It's not varying as much. It's still pretty jagged, but it's at least not changing its jaggedness. as I go. Let me turn it back on and let you see. See how it's not varying much unless I speak, right? When I speak, now it's like, hey, there's this other sound going on. I don't know what that's about. So coherence drops for the frequencies of my voices, right? That's sort of a slow averaging. You could do something called an infinite average, which is generally not advisable, but that just basically means it's going to average for the end of time until you tell it to stop. So even I could do infinite averaging and talk, and you can see that the effects of my voice will not go away as quickly now. See that? Because it's averaging over infinity. So that moment in time when I was speaking becomes a part of the permanent record of this measurement.
Oh, so the changing of the time is just changing like the period of time that it's taking data to average?
Yeah.
Gotcha.
So you could set it to whatever you want. You could do it in seconds, 1 second, whatever. I tend to just do the slow averaging for most of my measurements. That tends to give me, you know, the stability I need, you know, and every once in a while I'll have to turn that off if there's something weird I'm measuring and I just need to see it happen quicker. But slow averaging is pretty good. Smoothing, on the other hand, has to do with how much detail is in the graph. So right now I have no smoothing, which means I'm getting the detail as much as Smaart can show me, as much detail as it can tell me. But, you know, if I'm trying to figure out if I need to do any EQ on this loudspeaker, for example, maybe I don't so much care about this tiny little dip and spike within a couple of frequencies, right? Because I'm not going to dial that in on an EQ, right? My EQ tend not to have that kind of resolution, so I don't so much care about that amount of detail. So you can use magnitude smoothing to kind of smooth that out. Let's just turn on 1/48 octave smoothing and see what happens. It's a little bit better. Let's try 24th octave. Even better. 12th octave. Still gets smoother. They go up all the way up to octave band. Right? So if I do octave band smoothing, then basically this becomes a really smooth line. Here's my rule of thumb for this. Do you remember last year when we talked about the concept of critical bandwidth? Does anybody remember that term? Does anybody remember enough about it that you could tell me kind of what it means? So critical bandwidth has to do with, remember when we talked about comb filtering, and we said that one of the ways to fix comb filtering is actually to make it worse. And by making it worse, you force those cancellations and reinforcements closer together. And then they fall within the critical bands of your hearing. And the critical bands of your hearing are really about the resolution of your hearing. So our hearing system has kind of evolved to be able to kind of reject a lot of spurious data, right? So if there's like a lot of dramatic changes happening within a really narrow range of frequencies, like what would happen because of some weird reflections or something, if that's happening within this critical band, your brain system is going to kind of reject that as an error, and it will correct that data. And so you don't necessarily hear that. You don't perceive those vast changes because of that. Anybody remember what I said the average critical bandwidth is?
I'm trying to look up.
It's about 1/3 of an octave. It's a moving target as you go across this frequency spectrum, right? It gets wider or narrower depending on where you are on the frequency spectrum, but on average, it's about 1/3 of an octave. And that information is really, really useful for a couple of reasons. One is that if you're thinking about doing frequency adjustments like EQ changes, I tend to, when I'm making frequency adjustments, I'm doing really wide band adjustments, because you could take that parametric PQ and you could narrow it down to like a laser notch and imagine that you're fixing some problem that you can hear, but you can't hear that. Your brain will reject that little laser notch as an error. And so I tend to try to kind of make at least third octave range adjustments. If the filter range that I'm adjusting is not at least a third of an octave, then there's not a whole lot of point in trying to do that, because that's, you know, not breaking through the critical band blind spot of your hearing system. Likewise, in Smart, I'm not going to waste, I tend to kind of set Smart smoothing at around a third of an octave. And there's a lot of people who disagree with me on that, because they say, yeah, but you're hiding a lot of information there. So yeah, I am. But what I'm seeing, when I dial in a third of an octave, I'm seeing a frequency response graph that is closest to what I'm hearing, to what I'm perceiving with my ears. Yes,
so the smoothing that it does when you're doing it, like you add it to a third of an octave, it's just averaging out the data in that third of an octave, right? It's not like picking one. Right. So if there was a frequency interaction that was happening there that would be reflected, it would still kind of be able to be like showing. Yeah, obviously, I mean, it would be lesser, but. Yeah,
I mean, we're still seeing pretty narrow dips, right? I'm seeing this little narrow dip here, this little narrow dip here.
So then what is the data that you're losing? Genuinely,
well, so you're losing, you know, let me turn on the 48th octave. You know, I'm losing, I have this little dip, I have this little dip. I'm losing the fact that it dips and then boosts and then dips again before it comes back up. When I average that out or smooth that out, I lose that extra little boost. But for my purposes, like if I'm trying to figure out what I'm going to do about that, if I decide that that's real, which at the moment I'm not convinced that it's real because there's a coherence dip lined up with that frequency response dip. But if I decide that it's real, and I decide that it's something I want to do something about, and maybe the thing I'm going to do with it is I'm going to adjust an EQ because I think that'll fix the problem, I'm not going to go in and adjust a big dip followed by another little dip right next to it in order to make that perfect. I'm not going to do that. I'm just going to do one filter that kind of does that whole little swath there. So I don't spend a whole lot of time getting myself all worked up about these tiny little jagged changes that I will not do anything about. Whether they are there or not, I'm not going to do anything about it. The main argument that I hear that is convincing to me about why you should avoid this much smoothing is that this much smoothing has a tendency to hide comb filtering. Okay? And if you think about that for a second, hopefully that would make sense to you.
Well, because like it's within the, like it's the exact octave that it smooths out.
Yeah, so it's hiding comb filtering, and it does do that. And if you have some comb filtering going on because of some problem with your system, then this will hide that. Here's my argument about that. So I say, you know what? If the third octave smoothing hides the comb filtering, it's hiding the comb filtering that I can't hear. And so why should I care about it?
Is it ever possible that if you have that like hiding in your graph somewhere, it'll ever get worse? Like, like I don't know, like a undiagnosed.
Yeah, I mean, you know, generally speaking, what I tend to try to do is I will put the magnitude smoothing at third octave, and then I'll do the phase smoothing at something more like 1/24th or something. Because that way, if I do have some comb filtering that is getting hidden by the magnitude smoothing, that should show up in the phase response graph, right? I should see the differences in phase there. And that helps me kind of spot that problem. So that's how I kind of compensate for that particular issue, is I want the magnitude response to show me data that is actionable. And I can't tell you how many people I've seen agonize over all these little minute differences in their magnitude response that, first of all, they can't hear, and second of all, they can't do anything about. because they don't have the tools with the resolution to do anything about that. So my opinion is, make the graph match.
Why stress yourself out?
Why stress yourself out over things that you have no control over and that you can't do anything about anyway, and you can't hear, right? You can't hear that problem. So why care about it, Generally speaking, you don't need to care about problems you can't hear. There are some exceptions, but generally speaking, if you can't hear it, you don't need to care about it. So that's my feeling on it. There are people who disagree with me, and that's fine, and we argue about it from time to time, but this is how I like to work. Okay, this bit up here at the top is called your live impulse response. And what this is showing, it's not showing it to me right now because I have it turned off, but what it will show you, because since it's a live impulse response, it only works when the system is on, but it'll show you how many times that sound arrived at the microphone. So let's turn it on and see what happens. Okay. So you can see there is a big spike right here, followed by another little spike there, and another little spike there. So every time you see a spike or a variation in there, that indicates another time that sound arrived. And, that would happen because of reflections, usually. Let me show you an example. I'm going to make some more spikes. I'm going to move the mic much farther away. Okay, so I've more than doubled the distance of the mic, which means I'm going to have to refine my delay. Okay, so I'm going to turn on the peak noise, refine the delay. It says 20 milliseconds. That sounds reasonable to me. It looks like about 20 feet. So I'll insert that. But now look what happened. It got quieter at the mic. So I need to either turn the mic up or turn the peak noise down on the input. Turn the peak noise down. Look at that. You see that little spike 45 milliseconds later? Where's that coming from?
A wall or something.
Yeah. So let me pan over here and let you see. 40 milliseconds would be about 20 feet to the wall and then back. 20 feet to the wall and then 20 feet back, if it's a reflection. Well, how far do you suppose that garage door wall is from my mic?
20.
It's about 20 feet. It's about 20 feet away, right? So the sound from the loudspeaker is hitting the garage door and then bouncing off the garage door and coming back to the microphone, and that round trip takes about 40 milliseconds. And the only reason we didn't see that before when the mic was closer is that the sound of that reflection had decayed more. And so it didn't show up as dramatic of a spike because it had tried to travel a farther distance. But now that I'm closer to that back wall, I see that spike better because I'm closer to it, okay? So let me turn this back on and let's see what happens here. Refine delay. So the other thing you should notice here is look at my coherence graph. You see how Smaart got a lot less confident the farther the mic got away from the loudspeaker? Why? Because it's now hearing all these other things. It's like it's hearing the sound coming off of all these different surfaces now, much louder. It's having a harder time figuring out which sound is the important one. So my coherence went way down. Not like sometimes this might be as close as you can get the mic to the loudspeaker. And in that case, you just have to deal with it. But I'm certainly, in this situation, I'm certainly not going to get too worked up about what's happening here at 1 kilohertz because I've got a really massive drop in coherence there, which tells me that the data is probably bad. That thing is probably not happening. How could you tell whether it was happening or not? Any ideas?
Listen.
Yeah, that's a big one, right? You know, here's your plug for ear training. So if it was really happening, you should be able to hear it. The only way that you'd be able to hear it is if you've done the ear training to be able to recognize that. Right? So if you've been really working on those frequency drills, that'll really help you tell the difference between, is that thing happening or is that thing not happening? You go stand next to the mic and listen to the pink noise, or put a piece of music in it that you know really well and listen to it and say, do I hear that dip? If you have that kind of trained hearing to be able to hear that and you don't hear it, then you're gonna say, okay, it really is a coherence problem. It's just bad data. There's some like weird interaction going on there and it's not a problem. If you go over there and you do hear it, then you're gonna say, okay, Smaart isn't confident, but I am because I can hear it. So I'm gonna do something about that.
Hypothetically speaking, if we weren't as confident in our ears, do you have an alternative method?
Yeah. So what you want to do is find a way to eliminate some of these surfaces. So one way, for example, could be to, like, one of the surfaces that's reflecting right now is the floor.
Are you going to lay on the floor again?
I'm not going to lay on the floor, but I can put the mic on the floor.
When we did Spring Awakening Quiet Time, you laid on the floor.
But you could put the mic on the floor, right? And that would eliminate that reflection. Because the direct sound would be hitting the floor and not coming back off the mic with any amount of distance. I could put the mic on the floor and up against the garage door wall. That would eliminate another reflection. So you can do some things like that that can kind of help eliminate some of the spurious data. But ultimately, if you do everything you can to make what you think is a good measurement and eliminate as many of those variables as you possibly can, and you still have a coherence dip in Smaart, then don't worry about it. Because obviously it is either not a problem, or you do not have the expertise or the tools to figure out if it is a problem or not. And either way, you can't do anything about it. Whether it's not actually a problem, or it's not a problem that you have the ability to decipher, either way, you have no control over it. So don't waste time on it. All you'll do is make things worse. Because if it is actually happening, and you don't know why, and you don't have the ability to tell the difference, then your attempts to fix it will just make it worse. Because you don't know what's actually going on. So leave it alone. Right? Okay. I think we've covered Smaart pretty well here. We're going to play with it a lot more. But any questions so far about any of that? Just kind of sort of makes sense? So here's something I kind of want to try, just for fun. This might blow up the whole Zoom meeting, but I just want to try it. There is a feature in Zoom where I think you can request to control this screen.
Yeah, it's in the view options.
Okay, Lance is requesting control of this screen. So I'm going to approve that. Lance, see if you can control Smaart here from home. Yeah, turn on pink.
I'm clicking. I clicked.
Oh, wait, Ryan is now controlling it.
Oh, Ryan.
Sorry.
Maybe too many cooks.
Oh, and keyboard shortcuts work too. That's great.
Yeah.
Wow. Thanks, Ryan.
Yeah. Okay, so Ryan, can you stop controlling and see if I can let Lance control it?
No, it's okay. I mean, I think it works for everyone, probably.
Well, I just want to make sure, so if we can come up with a process for doing this. So let's get, Lance, you try to control it now. Okay, Lance gets it. See if you can control it. Oh, that's so exciting. Okay, so here's what we now know. If for some reason we get to a point where I'm not allowed to bring any of you here, I can at least have you sit at home and learn how to control Smart. Super cool. Okay, that was something I wanted to try today, so that's good. Okay, so I'm now going to move on to FuzzMeasure unless anyone has any other questions about Smart. Okay, so let me get the mic back. Oh, the other thing I wanted to do before I move on to Smart is I want to give you a chance to hear what the mic hears, okay? So what I'm going to do is I'm going to mute my conference mic and I'm going to unmute the Zoom mic on for the Smart and let you hear that. So I'm going to turn on the pink noise and then I'm going to toggle that. Just let me know if this sounds reasonable to you.
Ryan, I think your mic is open.
Thank you.
Could you hear anything when I was doing that, when I was moving the mic?
No,
You couldn't hear like any of the pink noise at all?
I was silent.
Yeah, it was
Oh.
silent completely.
Weird. Huh. Okay, let me try something here then. Oh, maybe because of that.
Also, you should probably turn off the suppressed background noise.
Yeah, that's what I thought I had, but let me try. Okay, yeah, I got reset. Okay, so now let's try it again. So I'll do that, and let me reshare now. Okay. Now let's try it.
I don't hear anything. When you went to share, did you enable the share sound? Oh.
Oh yeah, is your screen share muted? That'd be funny.
It looks like you've just changed the input to come off input one.
Yeah, no, I'm not sharing the audio because I want to hear the mic. So I'm trying to use the Smart mic as the
Oh.
the mic.
But you're muting yourself. Like
No,
you
it's two different systems. Two different systems. So
There's
I
a
might-
screen share computer, and then there's the system that's his, like
I
Jason
see.
on there.
Got it.
So it's something to do with the Focusrite. So I've got to figure out how to get the Focusrite to send the right mic signal in. Let me see if I can figure that out. I'll share back with you so you can see what I'm doing.
Your ultimate audio engineering test.
Yeah. Let's see here. Device settings. Monitor controls. I wonder if that would be it. No, because I don't want to do that. I wonder if it would be in the audio MIDI setup. We'll put. Yeah, I don't see in there. Problem is Zoom has a hard time figuring out different inputs. So what I might have to do is put loop back on this thing. And then then it would definitely work because I'd be able to route the specific mic off the Focusrite into a software audio input that could then feed Zoom. So I'll try that for next week.
Couldn't you just do the same thing, making an aggregate device?
Not quite.
No, not quite, because I would have to, because the point is I have to figure out how to tell Zoom, which only knows how to listen to one thing, I have to tell it which one thing to listen to out of the 20 things that are coming in off this interface. So the aggregate would let me kind of link multiple devices together, but that would probably actually make it worse because then it'd have more inputs that it wouldn't know what to do with.
Does the interface have any mixing capability? Can you mix down to one track?
Well, yeah, but that's only for software that knows how to do that. So,
Loopback is probably the best route. I had an issue with my Apollo where the Apollo by default has the 2 mic inputs on it come out as 1 and 2 into the system, and then it has the monitor, the monitors that you're listening to outputs come back in as 3 and 4. And for some reason, Zoom was taking those inputs as well and collapsing them together and shooting them down the mic.
right.
So I can change that routing in the Apollo, but Loopback was also a solution to that.
Yeah, so maybe I'll try that next week. I'll put Loopback on this analysis computer, and we can try that next week and see if the folks at home can hear the mic. That should work, actually. I don't see any reason why that wouldn't work. Okay, so let's do FuzzMeasure really quick here. Some of you have seen me do FuzzMeasure before as well, so you've probably heard some of this spiel. FuzzMeasure, again, is a source-dependent system, which means it's dependent on its own source. There are templates here that you can use. I tend to like the classic one, but that's just me. So I'm going to hit classic and pull that up. And that gives me frequency response and impulse response, okay? Now, here's what you got to do. First of all, I'm going to open up this little sidebar because that's really helpful. And then we're going to open up this audio settings, which is this little button over here. And this is going to tell me, you have to tell Zoom sort of like which inputs and outputs, or not Zoom, FuzzMeasure, which inputs and outputs to use. So the first thing is the playback channels, right? So which outputs does it want, of the Focusrite, does it want to send its signal out to? I think number 1 is what I need. I think that's the one that's feeding the amp. If it's not, I'll find out really quick. I'll switch it. And then record channels. This is which inputs is it going to listen for? I actually want none of these. So I'm going to delete these because I'm using input 1. So let me get rid of these. Add another one here. Input 1, add, and then I'll delete number 3. So I'm going to use input 1 because that's where I have the analysis mic plugged into. And you see this calibration record thing? This is where you can load up the actual calibration files and stuff for the mic, which I'm not going to really worry about today, but that's where you can do it. Okay, so then to do this, to make a measurement, you're going to hit this button, this little plus button. And now, here's the thing. It gives you this little warning. It says, warning, this might be loud. This signal that FuzzMeasure uses as its reference signal is the best way I've ever found to blow up a loudspeaker. Like, if you want to melt a loudspeaker driver by overheating it, this is the best way to do it. It works really, really well. So I have melted a few loudspeakers this way. So you want to be super careful with this. But there's 2 things you want to do. This does what's called a swept sine wave, which means it's going to sweep through the entire frequency spectrum 1 sine wave at a time. So it sounds like it goes, right? So what I want to do is decide how long should that sweep be, okay? So I'm going to set the duration. In most cases, you can have it be pretty short and be just fine. But sometimes, particularly if you're going to try to measure reverberation time of the room or something, you might want to make your sweep longer so that it has time to kind of hear all that stuff. So I'm going to keep that short for now. And then the amplitude, this is the part you want to be really careful of, because this is how loud it's going to be when it comes out. And I want to start this pretty quiet because I really don't want to blow up this loudspeaker. So I'm going to start it at like -45 or something and see what happens. So I'm going to hit that. I'm going to hit the play button. Let's see what we get. Okay, that was really quiet. But FuzzMeasure still took it. Sometimes if it's too quiet, it'll tell you, hey, that was too quiet. I can't deal with that. But let me go ahead and delete that. I'm going to try it again and turn it up, because I think I've got some room here. I'll take it up to 30. And we'll see if you guys can hear this. Did you hear that?
Yes.
Okay, great. Okay, so that's it. A little sweet, right? So here's what I get. I get this frequency response graph that's currently set at 12th octave smoothing, and I get this impulse response graph down here, which tells me time. Here's the cool thing about it. This is actually a recording. So it recorded that sound when it came in on the mic, which means I can mess around with this data now all I want without having to make the sound again. So maybe I think, I want more smoothing than 12th octave. I could go over here to measurement, and, or sorry, might have to do it here. Oh, here we go. So I go to the graph. I forgot that's where they put it. So under frequency response, I go to graph, and I can say, show me this in 3rd octave smoothing. And it'll just do it, because it's doing it off of recording, not a live thing. I can do 6th octave. I can do none. And this is, you know, so I can play around with the data after the fact, which is pretty cool. And then I can kind of zoom in and out on this stuff. So I can, you know, kind of using the trackpad, kind of look at different parts of it to get a sense of what's going on. I can also do the same thing down here in impulse response. So I can zoom in on the impulse response and see what's going on. And I can kind of see the different spikes that it's seeing in the graph. The auto extents just kind of rezooms it back out. That's basically FuzzMeasure. Now you can look at this in lots of different ways. So there's all kinds of graphs that you can do. So I could add another one here. Maybe I want to see harmonic distortion. Could see the extent to which I've got a distortion going on. You could do, that's something you might want to do if you're like designing loudspeakers or designing equipment. You want to see what's going on there. It's not something I use very often. You want to see phase response. There's your phase response. That's a mixed phase response. Let's try minimum phase response, which is probably more like, you know, the real thing. At least what you would see in Smart. What else do we have? Oh, here's a cool one. FFT waterfall. So this shows you sort of a graph over time of the frequency response, over the time of the measurement, which is kind of interesting. I'm not sure I really understand how that works given the way the stimulus sound works, but there's probably some fancy math going on in there. But here's another one that's kind of cool, reverberation time. So this tells me the reverberation time per frequency of this room, which looks like about 1 second. This room has a 1 second reverb. It's pretty good, actually. We should probably sample this room. We could put it into a convolution reverb. It sounded pretty good. But that's kind of a lot of reverb for a class. I mean, you're probably even hearing some of that reverb on the mic here because you're getting those reflections coming in. So not an ideal situation for a room to try to talk in, but you can see that. FuzzMeasure will tell us all that. I didn't have to tell it to measure reverberation time before I made the measurement. I just made the measurement, and then I can tell FuzzMeasure, hey, show me this data in lots of different ways. Okay? So that's a really great advantage of FuzzMeasure, is that you just make a noise once, and then you can interrogate it for as long as you want without having to make the noise again. Here's what I tend to do with FuzzMeasure. So let me, I'm going to move the mic here back to my other spot. And then I'm going to measure again. Okay, now I've got two measurements, don't I? And you can see that's that spike from the back wall reflection now that I have on this one. But here's what's cool about it. If I hit Command and click on the first one, I can see them on top of each other, which is super, super cool. Why? Because, let me put this on and, yeah, it is equals. There we go. So if I zoom in horizontally on this, I can look and see the difference in time between, like let's say I had a mic close and a mic far away and I did this measurement at the same time. I can see the time difference between the close mic and the far mic. That is super helpful when you are setting up precedence delay systems. Because if you try to do that in Smaart, first of all, you have to have the sound going on a lot longer than you need to, but you have to basically use delay finder to try to figure something out and then not insert the delay. But this way I can just kind of look at it and say, okay, how much delay is there between these? Let's say that this was supposed to be a precedence system. And I wanted 5 to 30 milliseconds between these two sounds. Well, I can see that the first sound is hitting at around 8 milliseconds, and the second sound is hitting around 24 milliseconds. That's within the precedence window, isn't it? So what's 24 minus 8?
18.
16?
Is it 18? Is it 16? Oh,
16.
I think it's 16.
16.
I've been doing bad fast math lately.
I know, I'm horrible at fast math. So, all right, so 16 milliseconds, that's within the precedence window, right? There we go, so I can verify that that should work. So this is what I use FuzzMeasure for all the time, is when I'm trying to line up delays for my loudspeaker system, because I can superimpose separate measurements on top of each other. And I can even make all these measurements in all these different locations, and I can take the file home and goof around with it at home, figure out what I'm going to do about it, and then come back the next day and make the changes. Right? And then I just have to then I can just verify the changes, make sure they worked, and I'm good to go. So the downside here, obviously, is that, you know, it's hard to make a change and immediately see the result, because you have to then make another measurement, do another recording, then go through the interrogation process. But other than that, this is a pretty cool tool. So we will use this occasionally for things that it's good for. But most of the time, we'll probably use Smaart, because a lot of the things that I'm going to teach you this semester are going to involve needing to see immediate results. So we'll probably use Smaart most of the time. But that doesn't mean that Smaart is better than FuzzMeasure. It's just a different tool. And Smaart is a better tool for the kinds of things that we're going to be doing most of the time in class. Any questions about that? That's a real quick crash course. I just want you to kind of see the fundamental difference between these two tools. The other nice thing about FuzzMeasure is there's nowhere near as much sort of just like goofing around you have to do with it to get it to show you stuff. Right? Whereas with Smaart, you have to like do this whole song and dance of setting up measurement configurations and comparing inputs and pairs and all that kind of stuff. And you don't have to do any of that with FuzzMeasure. All you tell it is which mic to listen to. You hit the button, you get the sound, and then you've got the graph. And you can figure out later what data you want to see, which is kind of cool, I think. All right. So that is about it, I think, that I was, oh, the last thing I was going to tell you, this is sort of this will make more sense when you come in the room. But sometimes we'll use mic stands like this, but other times we'll use mic stands like this. And this is a cool mic stand because you can just like clip it to the back of a chair or something in a theater and then put the mic on it. But it uses a different thread. And so you have to put the little adapter in it. So let me show you what that looks like. I don't know if this will work, but let me try and zoom in here. Okay. That's as far as I can get. Oops. Okay, so you see that this clip has kind of the big thread for American microphones. Well, in Europe, they use this size, which is smaller. So there's these little adapters that you can put inside the clip which reduce the thread size inside. But one side of this has, can you see the little notch that's carved into that? Whereas on this side, there is no notch. Let me see if I can get closer.
We'll just take your word for it that there's a notch.
There's a little notch there.
Also, if you just look up European mic stand adapter, there's a little notch.
Yeah, the point of the notch is the little notch is used to get it back out of the clip. So you want that little notch pointed out from the clip. If you put the notch on the inside part when you screw that in, then you can't get the thread adapter out again. And that's pretty stupid. I can't tell you how many times I've had to figure out how to dig one of these thread adapters out of a mic clip because someone put it in backwards. Okay, so don't do that. Put it in so that the notch is pointed out, and then you can stick a screwdriver on that and unscrew it out of the clip. Okay, so just a little tip.
Why don't we just leave those on the like clippy mic stand?
Well, because they come off of these more easily, and when you take the clip off, the adapter tends to come off with it.
It'd be in the right direction, though.
It would be in the right direction. It is true.
If we felt really strongly, we could glue the 5/8 adapters onto the gooseneck clamps.
We could. That would be an interesting exercise for someone to do. But I'm less inclined to do something like that just because sometimes there are some things we have that would go straight onto this without an adapter. And so I wouldn't necessarily want the adapters to be like part of it. I'd rather you just learn how to use the adapter. That would be the better way. That way, when you encounter one out in the wild, you will know what to do about it when you see it. Okay, so that is your crash course in Smaart and FuzzMeasure. We will do a heck of a lot more with this stuff over the course of the semester, but this is the basic idea. Next week we'll play with it some more. We'll learn how to make point source arrays and use Smaart to help us verify that we've got display angles correct. That'll be what we do next week, and keep doing more and more of those kind of things. So any other questions before we finish up here?
Yeah. Are you gonna send out like a schedule for everyone as to when we're doing like when we're coming in?
Yep, I'll put it on the Canvas page. I'll figure out some way to do it on Canvas that'll make sense.
Oh, in 2 months I'm gonna forget. So.
Yep. Anything else? Any other questions? Okay, well then I think we are done for the day. So tune in next time when we'll do those point source arrays. And I'll see you all this afternoon at 2 o'clock on Zoom, okay?
Thanks, Jason.
All right. Thank you, Jason.
Thank you, Jason.
Okay, see you later.
See you later.